athletes, here we are looking at properties of logarithms, 6.5. So this applies for any positive numbers of mn and b where b cannot be 0. So if you remember from our exponent rules that we had some rules, namely if we had like b to the x and b to the y, when we were multiplying those, okay, we said that it was bx plus y. Okay. Since logarithms do represent an exponent, the answers to them are exponents, a lot of this rule is going to be analogous when we think about our product property. Okay, that when we have multiplication of log base b to the mn, if we want to split that up and write it as two separate logarithms, okay, that multiplication now becomes addition. The other exponent property that we had was our division. So if we had b to the x over b to the y, okay, that was analogous or equal to b to the x minus y. Okay, so now that comes to our quotient property for logarithms. If we have log base b, m divided by n, that division becomes subtraction when we split up our logarithms. Okay, and our power property, okay, comes from the fact if we had b to the x to the y, okay, well, we just took b to the x and we multiplied that exponent by y. So if we have an exponent in our logarithm, we can write that and drop it down in front, and that x now becomes a factor of log b to m. That's our power property. So we're going to utilize these properties in today's lessons. Sometimes we will be given multiple logarithms and we want to write them as a single logarithm. So we'll use these properties to go kind of left here. Or we'll be asked to have a single logarithm and we'll say expand them and write them as multiple logarithms. Okay, so our first examples here. So I notice that we are writing these as single logarithms. Okay, so if we have two logarithms here, notice they have to have the same base, so 5 and 5. So if I write this as a single logarithm, this addition is going to make us multiply our arguments. So log of 5, and now it's going to be 2 times 6. Okay, so 2 times 6 I can do and simplify and get log of 5 of 12. Okay. Here I have subtraction, so I should be thinking of division as I'm writing as a single logarithm. Again, checking we still have base 2, so log base 2 of 8 divided by 4. Well, 8 divided by 4 is 2, so I get log of 2, and we know that's 1. Okay, last one here. So here we got power rules and our quotient rule. So these factors, remember, need to go up as exponents here. Okay, so I'll break this up into kind of 2 steps. So I'm going to do that first. Notice I both have log b, so I'm going to be able to write it as a single logarithm after I have employed the power property. So now I've done that. Now I can write it as a single logarithm, base b, and 4 cubed is 64. Minus is going to change this to a division now that I'm writing as a single logarithm, and 2 to the third is 8. 64 divided by 8 is 8, so I get log base b 8. Okay. Here on our next slide, again, we are going to condense these into a single logarithm. Okay. So again, kind of how I think about this, especially if I have multiple logarithms, okay, those properties pretty much say anything that's a positive one is a product, anything that's a negative one is a quotient. Since these are all the common logarithm, I imagine there's a 10 here because nothing else is written. Okay, I can combine these. So everyone that's positive positive is going to be a product, and anything that is negative is going to be a quotient. So as I write my log base 10, since I have both, I write a fraction bar. Okay. Anything that is positive will go on the top as multiplication. So I'm going to get 9 times 2 to the third, because this 3 factor in front will come back here as an exponent. Okay. And I subtract log of 3, so subtraction becomes division. So now that I have condensed it to a single logarithm, I can write it simplified out. I'm just going to write it as log. I'm not going to write my base 10. Okay. 2 cubed is 8. 9 times 8 is 72 over 3. And if I simplify that, I get log of 24. Okay. Expanding this, notice I can expand even with my natural logarithm. So I know that's just representing log base e, but we don't write as log base e, we just write as ln. These same rules apply. Okay. So as I'm expanding, I kind of think of this inverse rule, and I think of, all right, since we're going the other way from the problem above, anything in top is going to be a positive number. Anything in bottom is going to get a minus sign. So in every term is going to get an ln. So I get ln of 5 positive plus ln of x to the 7th minus ln of y. Okay. I want to wait and make sure. Notice I have an exponent here, so I should use that property. So my final answer is ln of 5 plus 7 ln of x minus ln of y. Okay. So here's some more simplification here. Okay, so we're going to write each expression as a single logarithm. Okay, so as I write my logarithm, I recognize, okay, it's base 3, both base 3, so my single logarithm will also be base 3. Since I have a subtraction here, that's this one being negative, so that one's going to be on the denominator. And it's just written as a single logarithm, so I'm not writing it again. And my numerator is my positive. Okay, so as I simplify that out, 20 divided by 4 is 5. So I get log base 3, 5. Okay, so there's my final answer on that one. So now as I'm adding logarithms, okay, I notice I have a constant in front, so that is going to end up being a power, so I might just write that out. So I get log of 2x cubed plus log of 2y. Because it's addition, it should be transferred to multiplication. Notice both base 2, so I can do that. If they're not the same bases, we cannot write it as a single logarithm without maybe doing some simplification. So you get log of base 2 of x cubed times y. Okay, so there's my single logarithm. Now going the other way, expanding, I recognize how many terms I have. So here I'm going to see I have one term, or within my term, how many factors do I have? And I have another factor. So then that means I'm going to have to write at least 2 logarithms, one for the 3, one for the R4. Because they're being multiplied together, I will change it to addition. So I get log. My common log is base 10. It's not written. So log of 3. Multiplication goes to addition. Now I split it right as multiple logarithms. And I get R4. And that 4 has a power. So I need to rewrite that in front. So my final answer is going to be log of 3 plus 4 times log of r. Okay. So expanding the other next term, I have two terms. I have x and this y. So each one's going to get a logarithm base 5. Things that are positive, or in the numerator, are positive, so I get log of 5 to the x. Because y is in the denominator, it's going to be a negative log of 5 to the y. Always double check and make sure your bases are correct on your logarithms and you didn't forget them from the original one, and carry those over. Okay. So, like I said earlier, our natural logarithms, the properties are going to be the same as their common logs. So if you want to write these as a single logarithms, okay, we can employ those same rules. So I'm going to write this as an exponent and one single logarithm, fraction bar. Things that are positive in the numerator, that's 6 to the third. Things that are negative go in the denominator. Just again, if it's saying write as a single logarithm or natural logarithm, I better make sure my answer only has one single natural logarithm in it. Okay. Well, this is actually not completely done because we should simplify this left side. So 6 cubed, I end up getting 6 cubed is 216. So I get ln of 216 over 8. And that simplifies to ln of 27. That's my final answer. Okay, here, first employ my product property, so 3x cubed plus ln y. Well, I haven't written a single logarithm. I still have 2 written, so to write as a single logarithm. ln, addition, just change to multiplication. You don't have to write the multiplication because it's implied when they're right next to each other as variables. Our final one, okay, again, these fractions are just powers. So I'm going to get ln 3 to the 1/4 plus ln of x to the 1/4. So now as I write as a single logarithm, I get ln of 3 to 1/4 times x to the 1/4. Remember, fractional exponents are radicals, so we get ln of root 4 of 3 to the x because they both had the same power. So there's my single logarithm. Okay. So next step is using some of those properties and powers to write them out and simplify them. Okay. So if I know log base 2 of 3 is approximately 1.585, log 2 base 2 of 7 is approximately 2.807. How can I use these to evaluate these other logarithms? I can use my properties of logarithms. So notice I have a 3 here, and a 7 here, and a 7 here. Well, in order to do this, I need to expand this and write it as multiple logarithms. So I get log base 2 of 3. Division is subtraction, so minus log base 2 of 7. Okay. Now, by substitution, I know log of 2 base 2 of 3 is 1.585 minus, well, I know that log base 2 of 7 is 2.807. Okay. So this is going to be negative 1.222. Next one, so I'm trying to think, how do I get 221 with 3 and 7? Well, that's multiplication. So I can do log of 2 of 3 times 7. Well, since it's multiplication, I'm going to expand it and write them as 2 logarithms, but they will be added together. Okay. And now by substitution, log 2 of 3 is 1.585 2.85 plus log 2 of 7 is 2.807. So we end up getting 4.392. Okay, and our final one over here is log of 49, so I should think, oh, well, this is log of 2, and that's 7 squared. This can be brought down in front, so I get 2 times log of 2 to the 7th. Log base 2 to the 7th is, by substitution, is 2.807, okay, which I am going to get as 5.614. Okay. Our next examples is trying to figure out how did we get from these previous slides, where do we get 1.585? Okay, how do we get 2.807? Earlier in the chapter, when we were expressing these as logarithm, express these and asked to evaluate them, we said something like this, and we said, well, this could be written as exponents, and this is 2 to the x is equal to 8. Well, can I write 8 as a power of 2? Well, sure, I can. I get 2x is equal to 2 to the 3rd. Okay, and so I can see that I get x is equal to 3. Okay, so something else that we want to think about is, well, what happens when we can't get these to be nice numbers? Okay, well, one property that we can do is I'm going to go ahead and say, okay, I know that this expression is equivalent to this expression. Okay, well, in our calculators, we have natural logarithms, ln, and we have our common logarithm, log base 10. So what I'm going to do is I'm just going to take the common log of both sides and put it here. Okay. There's a property of inequality that says we can take the log of both sides. So when you do the log of both sides, notice I have an exponent here. So this can drop down in front. So now I have x times log of 2 equals log of 8. Well, if I want to get x by itself, because that's what I'm trying to find, okay, there's multiplication here, so I can divide this side by log of 2, divide this side by log of 2. Anything divided by itself is 1, so 1 times x is just x, equals log of 8 over log of 2. So now if I use my calculator, okay, I can go ahead and type those in. And I can say log, turn it on first, log, there's my log button, of 8. So notice when you type in log, at least for many calculators, you can't change that base. So in order to do that, we're going to type log of 8 divided by log of 2, and we'll see that it is 3. So that right there is what we call the change of base formula. Okay? That if you have log base b of m, that is the same as log of anything you want. Okay, so typically we're going to make this 10 because that's the one that's common on our calculator, or we might choose e and do our natural logs. But notice the m, it's our larger value where b is our subscript. That larger value is always your logarithm on top, and your subscript ends up being your logarithm on the bottom. So if I wanted to evaluate log of 6 base 6 of 12, right? This is saying 6 to what power is 12? I know 6 squared is 36, 6 to the first is 6, so it's somewhere between 1 and 2. So to evaluate this using my change in base formula, I'm just going to write this as log of 12 over log of 6. So now as I grab my calculator, I can do log of 12 divided by log of 6. I get the 1.386. or 7. Okay. Notice if I did this with natural logarithms, ln of 12 divided by ln of 6, as long as those are the same bases, we'll get the same answer. Okay. We get 1.387. You only want to use just change bases there if you're doing change of base formula. Okay. So if we want to evaluate log of 3 to the 8 using common logarithms, we've already done that. Or actually we haven't, we did 2 to the 8th. So then this is going to be log of 8 over log of 3. So you type it into your calculator, you get approximately 1.893. That should make sense because I know 3 squared is 9. I'm trying to get to 8, so I'm really close to being squared, while 1.893 is about 2, or close to 2. So that seems like a reasonable answer. Our last one, we're going to do log 24 divided by log of 6. These are just our common logs, base 10. So as I type that in my calculator, I get 1.774. That concludes our notes today. Please highlight any questions and bring them to office hours.